Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
So our favorite magician may be Houdini. Now he was mostly a showman. He did standard things that all magicians do, even I can do, but he was a great showman. So one of the things he did, which we'll try to demonstrate, was escape from handcuffs. So I will need one of my assistants here. Okay, and what he's showing there and on the right is Shanghai handcuffs. And these days they are made in China. But the locks, in fact, are made in the US. They're good old master locks, maybe. Verify they're master locks, right? Need a key? Okay, let's put those on. And we could make these as tight as we want. Being a magician, it doesn't matter. Okay. Okay, let's hold on to the keys. That's always important, except I do bring bolt cutters if we need them. Now, when Houdini did this effect, he would struggle. He claimed he had to dislocate his wrists, et cetera. So he would make it look very difficult. But of course, he didn't have to do that at all. He could get out very quickly. Okay. And of course, one of the interesting things about magic is you always want to know how it's done, right? And in physics, we reveal that, of course, how things are done. In magic, we don't. We often let the audience participate. Put out your arms, please, your hands. We have never met, is this correct?
That's right.
You want? You can believe it or not. Take your pick. Okay. Ah! Well, I don't want you to get out. That would spoil the effect. I have to show you how difficult it is, even to put them on. Okay. Well, you have fat wrists. Actually, that's one of the secrets. If you use fake wrists, you can get out of them very easily. That's one of the many methods to do the effect. Or, of course, you can use fake locks. We'll let you decide which is which. I won't put this on so tight, because I don't think you can get out in any case. Okay, there you go. And now we just can figure out how that's done. And we'll leave the keys there. Now, when Houdini did this, he was an expert locksmith. He had lock picks. And in fact, back in the days when he did that, there were only about 10 locks in the world, so he would have keys for all of them. Hate to spoil the illusion. It's a little more difficult these days. Okay. He also often performed naked. I'm not doing that today. I don't do it in my classes either, only for under special arrangement. Okay, well, we want to show that science is interesting and fun. Why would students want to study science? Well, if they're scared of science, they're certainly not going to study it. So we try to, in our classes, many of our classes, make some fun of science, or make it interesting at least. So we have to convince others, especially students, that science is not to be feared, as many believe. It actually has some very interesting aspects that we should all know about, and in particular, nature. And that's what I'll be talking about. Well, the magic capital of the world is here in Michigan. Down by Coldwater, a nice pleasant drive down 12. It's Cologne, Michigan, and yes, it's named after that body part by a doctor with a great sense of humor who used to summer there. And they have a magic festival during August, a great place to take kids. And I strongly encourage you to visit that, where you'll see real professional magic versus what I do. Okay, One of my inspirations was Mr. Wizard. He introduced me to science. Yay, let's hear Mr. Wizard. He was from, are you out yet? Are you out yet? No, okay, you're still wearing, okay. Someone want to give him a lock pick or a key? Okay, Mr. Wizard, so he really embodied making science interesting, and there were cute girls also. I thought I could meet girls this way. Anyway, this was in the 50s and 60s. Another favorite was Julius Sumner Miller, who was on the Steve Allen show. Steve Allen was interested in science. He did some amazing things, and again, got me through graduate school. Be average. Anyway, if you know him, then you should be retiring shortly like me, or are retired. Okay, well, I got started in magic. One year I asked Santa Claus for a BB gun. Instead, I got a magic kit. And it was actually some things that could be dangerous, but not really dangerous. But from that, I postponed the BB gun until I was older and learned some magic, and that sort of got me started. Now, of course, there are some differences between normal folks and magicians. So here are some famous magicians: Chris Angel, Lance Burton, David Copperfield. Scientists, I'm a scientist, are sort of like magicians. We reveal our things that we do, our acts. We do experiments, we publish, give lectures, etc. But you notice these fellows dress a little differently. Expensive jewelry, fancy clothes, they work in Las Vegas, and they get paid a lot more. They're all millionaires, by the way. Okay, well, scientists and magicians also have some commonality and differences. Magicians use attractive assistants usually, either male or female. Usually a spouse. They must learn the magic, the magician's assistant, often wear leotards, smile a lot, be a distraction in general, and fit into confined spaces often. Scientists, well, our spouses need not learn scientific techniques. No dress code, except my wife likes Italian shoes. Smile occasionally, only when justified. Jokes are funny. Need not fit in confined spaces unless they're the spouse of a graduate student or assistant professor. Especially on North Campus housing. Then you have to fit in confined spaces. Okay, well, scientists, we use graduate students as assistants. So here are my assistants. They work long hours. They need not wear costumes, just safety glasses. These are superconducting magnets. So these are magic. What's magic about them? Well, you know, most wire, when you pass current through it, generates heat, and that uses up some of the energy you're supplying. Well, I have here superconducting wire. When this is cooled to low temperature, so here's some very low temperature stuff here. This is liquid nitrogen. Watch out. So this has normal resistance, but when it's cooled to cold temperatures, it loses all its resistance. I can put a current through here with 100% efficiency. It uses no energy. So these magnets, once powered up in our experiments, we turn off the power supply. They will run for months with no power supply. Now, if we could do that with transmission lines, we could save 15 to 20% of our electrical energy. If we could have motors using this type of wire, we would save a lot of energy. The only problem is you have to cool it. So one of the holy grails of our scientists in material science is to make superconducting wire that's superconducting at room temperature. So we're waiting for that. Stay tuned. We're up to liquid nitrogen temperature and beyond, which is pretty amazing, but we still have a ways to go, but we're getting there. Magicians take an oath not to reveal magic except to other magicians. Scientists, we reveal everything to everybody. Okay, we publish our work. Magicians are allowed to lie, deceive, use secret collaborators, cheat. You might hear a magician say, "We have never met," correct? Or, "I have here an ordinary deck of cards." All lies. Okay? Scientists can't do that. We must never lie or deceive. A few have, and they've been reprimanded for that. Okay? All our collaborators are known. I publish a list of all my collaborators. Now, in this talk, you have to be careful. Either I'll be the great Federico, so everything here on magician apply, or I'll be Professor Becchetti and must tell the truth at all times. You'll have to be the judge. One of your challenges for the day. Okay, but remember, the main difference between scientists and magicians. Magicians know what they're doing. When they pick a card, when you pick a card, they will know your card usually. Okay? So here's Marie Curie. She's a scientist. She will be doing an experiment. She's going to mix these two chemicals together and see what happens. She may not know the outcome, and I would advise wearing safety glasses in that case. Okay, we do experiments as scientists. You put an assistant in a box with a chainsaw, the magician should know the outcome. That's not going to be an experiment. Okay? Scientists, we would not know the outcome. We would do the experiment. Would not use a live assistant, of course, but would, and that's important. In fact, as a scientist, I welcome an unusual and mysterious result I don't understand. I love that. I don't want to know the outcome. Why would I do the experiment? Okay, so that's one of the main differences. We do this experiment, we do this effect in our summer class where we just cut off arms and restore them. Okay, we can't afford the big saw. Okay, now there are theoretical physicists or scientists who claim they do know what they're doing. They are called theoretical physicists. They claim that their theories will predict everything that we want to do. Now this is Professor Veltman from U of M. He got a Nobel Prize, so there's some credibility there. This is Professor Kane. He's made a lot of predictions that are now being tested over at the LHC accelerator in CERN, and we'll soon know whether he's right or wrong. Okay? But both claim they know what they're doing, of course. So we have to be careful, though. In nature and in magic, we have a lot of illusions, things that defy our own senses. And is seeing believing? Can we always trust what we see or hear, especially here in political ads? But that's neither here nor there. We'll see in 2012. Okay, but can we trust what we see with our senses? Well, here's some optical illusions. Now, if these make you sick or queasy, don't look at them. Okay. Okay, which is longer, B or A? B or A? Well, you probably know the answer. They're both the same. How much darker is square A than square B? They're both the same shade of gray. This is an illusion done at MIT. Now, you can win money on this one. Anything moving there? No, there's nothing moving there. Anything moving there in the middle? And you see that in the handout more clearly. No, there's nothing moving there. Magicians use this effect all the time, both the color and illusions. So which is longer, top or bottom? Now which is longer, top or bottom? And I'm a magician, come on, you know? Yeah, they're the same. And here we're using both color and optical illusion. So here's another one. Maize in blue. Okay, notice the order. Blue is over here. And magically, they change order. Not impressed. A tough. Hey, you got in free. Come on. Okay, not impressed. What if I do that? Better? Okay. Okay, so magicians use optical illusions all the time. So we'll do another one here. So watch carefully. Were you watching my sleeves, my hands? Huh? You were watching? You really were watching? Huh? No, you weren't watching carefully enough, maybe. So be wary of magicians wearing baggy sleeved coats. They can do all kinds of interesting things. Psychologists are very interested in how magicians fool people and how nature fools people. There are books written. There's a society now that's studying this, and this is a wonderful book that combines both magic and these things I've been showing, called Sleights of Mind, Neuroscience and Magic. There are a lot of magicians actively working with neuroscientists now and how they fool people. As we know, magicians like to levitate things. The reason for that is that gravity, as we'll see, is a very weak force. Even though we live on this big Earth, and it's important to us, it's actually the weakest of all the forces. So it's very easy to levitate things. This is a little globe. Again, I can't afford the big one. but it's being levitated using magnetic field. Magnetic fields and electric fields are millions of times stronger than a gravitational field. So here's an electric field demonstration. As you know, like charges repel, so we're going to charge this up. These plates will become charged the same as the sphere. Easy to levitate things if you know how. The other strong force is This is why we have assistants, to do the dangerous things. Now this one over here is really dangerous. It's going to use a magnetic field and show you how strong a magnetic force is. And again, we use an assistant for anything dangerous, of course. So here's our lovely assistant. We know that aluminum cans are pretty robust, except when you apply a strong magnetic field. Again, I'm not going to go near it. Okay, you might want to plug your ears.
2, 1.
That was a magnetic field in action. And of course, being green, that can will be recycled. So I'm going to do one of the most amazing experiments ever done. It was done in Pisa, so you might know it's Galileo. Now my relatives come from a town just down the road from Pisa. They built a tower also, but it's straight. No one goes there. Okay. So just like demonstrations that don't work and are remembered, building a tower that's crooked is a mistake that has some value, I guess. Okay. So this is what Galileo did. No, actually, this is what Aristotle did. Aristotle said that light things fall slower than heavy things, which is true, except Galileo said, aha, take away the air resistance. So same mass, less air resistance. Oh, I even beat it. Okay. They fall the same. Make this infinitely small. Fall the same. Now this is an experiment that got Galileo into trouble, which is why it's so amazing. Is the Earth moving? Obviously, according to the clerics at the time and others, the Earth is not moving, but in fact it is moving. And of course, when I drop it, everything is moving. But we cannot tell whether the Earth is moving doing this experiment. Well, that starts the theory of relativity in physics, which Einstein is going to later exploit. It also shows you that there's something weird about gravity. Okay? And we'll show that. In fact, later, of course, Einstein is going to exploit that. So what Galileo showed, that everything falls the same. The Earth, you cannot tell if the Earth is moving or not. In fact, the Earth is moving around the sun. This experiment doesn't tell you that. And that introduces relativity, about relative motion and things. Also that the horizontal and vertical motions are independent of each other. They don't talk to each other. Things fall at the same rate in a gravitational field, whether they're moving horizontally or not. So what about this light beam? I just said if we make the mass 0, maybe, would you expect the light beam to fall in a gravitational field? You probably wouldn't expect it, but it is. Okay, so we have to invoke something that Einstein invoked, and that's called the equivalence principle. So pretend you're in an elevator here. Pretend this is a giant elevator. We're not on Earth, and this elevator is accelerating upward. And now I do this experiment. What's going to happen? The same thing that would happen in a gravitational field if this room is accelerating upward. That's called the equivalence principle. Einstein claims everything that you would see in an accelerating elevator is going to be the same that you would see in a gravitational field. They are equivalent. So if you were in an elevator, then if you're on Earth, you see the apple fall. If you're in an accelerating elevator, you see the apple fall exactly the same way. So what about light? So if you're in an elevator or a rocket ship and someone shines a beam of light across, if you're outside, the light goes in a straight line. If you're in the elevator, what would you see? Or the rocket ship, you would see the light bend. Einstein claims that this is what you'll see here on Earth, also since it's equivalent to being in an accelerating elevator. This is actually the prediction that made him famous in 1919 because the experiment was done with a solar eclipse that showed that starlight bends around the sun. Now we have lots of examples of light bending around galaxies and other things. This is an image of some astronomical object being lensed by this gravitational field of a galaxy in the front here. So we think that light travels in a straight line, but not in a gravitational field. It bends. In fact, in a black hole, the light bends back to itself and never escapes, hence the name black hole. And we know those exist, all based on this kind of magical physics called the equivalence principle. And this is what made Einstein famous, not his E equals mc squared or other things. But of course, in dealing with the equivalence principle, Einstein also said, well, there's some other things that clean up physics, solve a lot of problems. One is that all observers should never measure the speed of light to be greater than 3 times 10 to the 8th meters per second, a constant. And it doesn't matter whether the light source is moving or not. So if this laser was moving at half the speed of light, the light that you would measure coming out would still be at the speed of light. If it was moving at 9/10 the speed of light, the light you would measure coming out would still be at the speed of light. But someone riding on the laser, what would they measure? They would also measure the same value for the speed of light, a maximum. How can that be? Well, Einstein says the two observers must not agree on distance or time. Remember, speed is distance over time. So the distance and time have to be relative to the motion of the observers, and that's the theory of relativity. They also will not agree on the mass of the laser if it's moving. They will get different mass. How can that be? Well, if I move this fast enough, you think I could make it go faster than the speed of light? No, I can't, because its mass is going to increase, as shown in the graph on the right. As I approach the speed of light, the mass increases such that I can never reach the speed of light. Now, in nuclear and particle physics, we deal with this all the time. We have to include this effect. And how much goes into the mass as I increase its energy or speed? Well, that's given by Einstein's famous equation, E equals mc squared. So that's where that comes from. When you add energy to something, you increase its mass by that amount. And it can go backwards. You can take mass and convert it into energy. And we do that in nuclear and particle physics all the time. So Albert Einstein, here's a book of that name, is our cosmic magician. Far better than anything I can do. And he used just pure logic, as we saw, to deduce many of these things, including the equivalence principle. Okay, so in nuclear reactions, we are always converting mass to energy and back and forth. We do this on a day-to-day basis. Okay, another interesting prediction is that there should be this weird stuff called antimatter. Okay, I grew up in Minnesota. We had some nasty mosquitoes back then, but they weren't antimatter mosquitoes. So what's antimatter? Antimatter is when you create matter out of pure energy, you must create two forms of matter. The normal matter, like an electron, and its cousin that has all the opposite properties, except they both have mass. So a positive electron, called a positron, has positive charge. The normal electron has negative charge. When you convert energy to mass, pure energy into mass, you can expect to produce both matter and antimatter. In fact, it's predicted that both should be produced. So how does that work? Well, let me show you first a nuclear reaction. This is a nuclear fusion reaction. It's the reaction that powers the sun. So here I have two protons in the sun. They're going to come together and fuse. And then what happens here when they, oops, I hope you can see that. You get a lot of energy, for one thing, and you get out another subatomic particle called a helium. And the mass of this helium is less than the mass of the 4 particles that made it. And where does the energy go? It's the energy made in the sun, heating us today somewhat. Okay. Okay, the other thing we do, and we do this routinely in the laboratory, and I just mentioned here we have Mr. Einstein. He's made of normal matter. And here you have anti-Einstein. He's made of antimatter. Now they meet in a Starbucks or someplace down the road. And what happens there, energy is released, but only energy. Oops. Yeah, there they disappeared altogether. Yeah, they're gone. Up there somewhere. Okay. And again, we do that routinely in our research. Here's an interesting way to make new particles. You collide matter and antimatter, forming pure energy, and out of that pure energy can come all kinds of new particles. And that's what's done at Fermilab. In fact, the top quark was discovered there by groups including U of M, high energy group. So at Fermilab, they shoot protons on antiprotons, shown over here. Right here is pure energy, and out pop all these new particles, where you now go back from energy to mass. And this is a way you can make all kinds of exotic new particles. This is also being done over in the new CERN facility. This is basically a recreation of the Big Bang. Okay, so let's look at the Big Bang. So, problem puzzle. If the universe started out as the Big Bang, how were all the galaxies and you and I and other things there at time 0? And what happened to all the antimatter that was produced at the Big Bang? Remember, the Big Bang was just pure energy to begin with. Okay, so there should have been equal amounts of matter and antimatter made. Today, almost every one of you, most of you, all of you, is made of matter. You can shake hands without annihilating your friend. Okay, well, how do we know there isn't matter or antimatter in the universe? We see colliding galaxies, for example. You might think, well, we could have galaxies made of antimatter, and we wouldn't know that whether they're matter or antimatter. In fact, if you look at the atomic spectra of a galaxy, it's going to look the same whether it's made of matter or antimatter. But we see colliding galaxies now with the Hubble telescope. We don't see galaxies colliding that annihilate each other. So they're made of matter. Every collision we've seen shows that the galaxies are made of matter. What happened to the antimatter? This is one of the great mysteries of physics right now, and we'll get somebody a Nobel Prize that can figure that out. Okay, so where is all the missing matter, antimatter, at the time of the Big Bang? Remember, the Big Bang started off as energy and converted into mass. All the galaxies were energy at one time. One of the interesting things about gravity is that even antimatter has positive mass. Even though antiparticles have all opposite charge and opposite spin and things, antimatter does not have negative mass. Now that's a bit weird to me, maybe not to my theorists, but we don't have negative mass. Everything in the universe is mass. Okay? Even the antimatter has mass. So mass is strange, gravity is strange, and Einstein studied that and explained a lot of that. Okay, so we just saw how the sun makes energy by fusion, conversion of protons into other elements. That's what powers the sun. So now we can calculate how long the sun's going to last. You should be concerned about that, because in 1900, before the advent of nuclear physics, no one knew where the sun got energy. Now that would be kind of disturbing to me, because if it was chemical reactions, it isn't going to last very long. Okay? Nuclear reactions, fortunately, are 1 million times more energetic than chemical reactions, so we can predict the sun is going to last more than the weekend. More than our lifetimes, and more than probably the lifetime of the Earth itself. So that's important to know. So we'd really like to get the energy source of the sun, which is nuclear fusion. Forget about fission and use fusion. So here's a fusion reactor. Unfortunately, fusion reaction has always been 30 years away, starting in 1960. So we are getting closer, but it may be a non-converging series. But this would be the ultimate solution. No nuclear waste to speak of, safe energy, and totally green. That's the goal of a lot of our fusion energy scientists. But stay tuned for another 30 years. Okay. Now, Ford at one time thought we could solve the oil crisis with atomic cars. This was, I think, at the auto show without the reactor, but probably not going to happen. Okay. In fact, if you buy an electric car, about 20% electricity will come from nuclear power plants. So they are sort of atomic power in that sense. Okay, I just mentioned that matter and antimatter annihilate each other. When they annihilate each other, they produce high-energy X-rays that can be imaged. These are called gamma rays. Over at U of M Hospital, we have a group that is an expert in positron emission tomography. Positrons are anti-electrons. They're a form of antimatter. When they meet an electron in the body, they annihilate. So we can dope a person with radioactive sugar, a sugar that emits a positron. That sugar will go to physiologically active sites, including cancer tumors. And because we can detect nuclear radiations at a very low level, we can detect the location of a cancer tumor before it's ever seen in an X-ray or a CT. So here's something from GE. This person has several cancer tumors that no good radiologist even would detect, either on an X-ray or a CT. However, here's a positron emission showing precisely where those cancer tumors are located based on the fact that we have this antimatter-matter annihilation that can be imaged very sensitively. The amount of radioactivity injected is minuscule, very small, very safe procedure. As we know, most cancer can be cured if it's detected early. So if you hadn't had your colonoscopy or breast scan, please do so as soon as possible. If detected early, any tumor can be basically cured. And this is now the new modality for early detection of cancer. It's a bit expensive right now, so there's issues with insurance, et cetera. But our group at U of M is trying to bring the cost down. And this is another area of active physics called nuclear medicine. And nuclear medicine, amongst other things, is mainly geared to detecting cancer at an early stage using nuclear techniques. Okay, this area I happen to work in also. Okay, so today you probably will, or sometime in your life, you'll probably be in a scanner, either a CT scanner, which uses X-rays, discovered by Professor Röntgen in Germany in the 1900s, or more recently an MRI scanner. This is a big superconducting magnet again, like the one I showed earlier. And all these techniques are going to save literally millions of lives here in the United States at some point. And these are all spin-offs of basic physics research. Okay. All right. So what Einstein showed was that we live in a multi-dimension universe. And in fact, we can illustrate that. So here are two glasses. I couldn't use beer. We're not allowed to do that here. But they look like they're maybe 2/3 full. But that's because you're only seeing two dimensions, the area. And the area is, in fact, about 2/3. But in terms of volume, they are, in fact, less than half full. Because you were missing the third dimension, which is the 4-back dimension, which you need to calculate volume. Now, of course, the extreme case is martini glasses. So Mr. Martini was either a magician or a profit-oriented person, because when you get a martini, I emptied these last night, and you buy your martini, especially when you have olives in them, they look like they're pretty full. In fact, they're only half full. That's why bars love to sell you martinis. Okay, I like them too. But I'll insist, fill them up, please. Oops, I can't do that. Okay. Okay, so again, we have to get rid of that. Now, of course, as a magician, that's, oops, oops. Okay, let me get rid of that. What's going on here? What is going on? Oh, there we go. Never know. Darn. Okay. You're laughing. What are you laughing about? Well, this semester is the semester of water, right? Well, water, as we know, has very magical properties. We learned about that in one of our lectures. It can do amazing things, so let me sort of demonstrate that with what I have here. I want to make sure it's not too full, just full enough. Okay, we got it there. Okay, gotta be real careful. This is a magic Panera glass. So again, liquids have a lot of interesting properties. They can do something called a phase change. You know what a phase change is? It can go from a liquid to a solid. And in fact, there are 12 or more versions of ice. One of the interesting properties of water, as you probably know, is that lakes freeze from the top down, hence life can survive. Most liquids freeze from the bottom up. If water froze from the bottom up, you and I would not be here, nor would we have evolved from sea creatures. They wouldn't have existed. Okay, so water in itself is magical. Appreciate that. Unfortunately, here in Michigan, we are surrounded by water. Fresh water. Wonderful. Okay. Okay, well, Einstein says that time is relative because we live in not a three-dimensional world. I showed you here that if you look two-dimensionally, you don't see the third dimension. That's a hidden dimension, the third dimension here. Right now in this room, you think you live in 3 dimensions. Front, back, left, right, up, down. No, you live in 4 dimensions. Time. That is, time is different in the front row versus the back row. It depends on the coordinates of where you're sitting. It's a 4th dimension. It's too small for you to see, but it can be measured with scientific apparatus. It depends also on the motion of the observers. Okay, Einstein showed that dimensions and time are all relative to the motion of observers. So here we have 2 twins, born the same time, aging at the same. One becomes an astronaut, goes to U of M Aeronautical School, and gets in a rocket ship, goes to a star 30 light years away, and on Earth she takes a trip that's 30 years. She's traveling near the speed of light. Einstein predicts that her clock will slow down. Her biological clock and her physical clocks will all slow down. Theory of relativity. She will come back 30 years later, according to Earth time, and that will be her twin sister. And this actually would happen. Now, we've done the experiment. So a couple of my friends booked a flight around the world through Hawaii, Tahiti, Australia, taking with them 2 atomic clocks, or taking 1 atomic clock. They left the twin atomic clock back here on Earth. If you remember, twin atomic clocks, if you come back in 1 million years, having started them off together, will agree in time to within 1 second in 1 million years. We had a lecture on that a few weeks ago. Okay, so he took one of his clocks in a plane, that's going to Hawaii, I guess, went around the world in a couple directions, and compared the time differences of these 2 atomic clocks, and here are the data, you don't have to worry about that, and indeed, the atomic clock on the airplane aged slower than the atomic clock left on Earth. It was the twin paradox. And we have to use this in our experiments all the time. We have to account for time, this so-called time dilation. In fact, I can demonstrate that here with a Geiger counter. You will hear particles going through the Geiger counter. Those are cosmic ray muons that would never reach the Earth because they only live for a microsecond in outer space in their own time frame. But since we're here on Earth observing them, we're in a different relative frame. They are traveling near the speed of light. Their clocks to us slow down. So this is the twin that doesn't age coming down here. So we have a twin that isn't aging coming down here to Earth. In their own frame, they're only living a microsecond. So your GPS, which is accurate to within a few feet anywhere on Earth, has to use relativistic mechanics to do the calculation properly. Okay. So here's volunteer. Find a number and tell me which cards they appear on. Just pick a number and tell me which set of cards they. Do you have a set of cards? A. Just on A? Only on A? Just on A. The number is 8, probably. Okay, do you want to pick one?
B.
B?
D.
B, D?
E and F.
Oh my God. Okay. And F?
Yes.
53?
Yep.
Want to try another one? You. E? Just E? No, it can't be just E. Put your glass, huh? E and D? D and E, okay. Is that it? Oh no, another hard one. Okay, is that it? 49. Okay, well this is mathematics now. With only 6 cards, you can make at least 69 different combinations, unique combinations from all those cards. So you only need 6 objects, 6 cards in this case, to make a large combination. So how is this related to physics? Well, in the 1950s, when we had particle accelerators just coming on board, we were discovering dozens of subatomic particles. They had all kinds of strange properties. We couldn't make heads or tails of what they were, but eventually systematics emerged, that there were symmetries appearing. And in fact, we now know that with only 6 quarks, up, down, charm, strange, top, and bottom, and 6 things called leptons, we can create all the particles we need to create subatomic particles. So with only these 6 particles, like the card effect I showed, with only 6 objects and their antiparticles, you can make all the subatomic particles, a whole zoo, hundreds of subatomic particles, only made of these quarks. Now what's strange about the quarks, they're never seen by themselves. They're only seen in combinations. And they individually have fractional charge. Most charges are plus and minus 1, 2, 3, 4 integer charges. Quarks have 1/3, minus 1/3, 2/3, minus 2/3, etc. Fractional charges, we've never observed fractional charges, but we really believe quarks exist because they explain so much. But they don't exist by themselves. Okay, here's an effect I'll do. We're going to make a quark system. Let's see if I can do this. Project ahead. First of all, here we have all the quarks. And I'll just put them out here. They're all different. And we all have a favorite subatomic particle. And I think you might pick one that I like. So I'm going to make a prediction here of what particle you might predict. Let me see. Okay. Since people can see me over there. Okay. I'm going to project ahead in time. Some theories predict you can go ahead in time, by the way. That's not what I believe in, but we'll try it. So I'm going to predict a quark system. Okay. And so let's have a volunteer. Pick a quark, any quark. Tell me when to stop. Stop? No, you can just tell me when to stop.
Sorry?
Well, just tell me when to stop. This one? Don't look at it, though.
Okay, that one.
That one? This one? Sure. Not adjacent one? Okay. Okay, oops, I got to do my, use my wife's headband here. Hope she didn't miss it this morning. Okay. Okay, another pick one. You and the handcuffs.
That one.
This one?
Yeah.
Okay. These headbands. You bought a good one. Usually he buys them from Kmart. Okay, another quark. Tell me when to stop. Yeah, you can just tell me when to stop. This one? Oh. This one? This one? Just say stop. This? Oh, I got to point at it. Okay. That one? That one? That one? Okay, thank you. That's it. Okay, I'll let you look at it. I don't do this usually. Okay, look quick. Okay. Okay, so we had all these quarks picked out. I even let you look at one. Okay. Huh? So I predicted a sigma plus. That's my favorite subatomic particle. And you picked an up strange, you were strange, a strange and an up quark, okay? So remember that. See, what do we say? Up, strange, up. And let's see, and I picked a sigma plus, that is my favorite. Okay, let's see. So this is the Zoo of Subatomic Particles, and we look over here, sigma plus. Up, up, strange, up, up, strange. Thank you. I knew. Usually it's a proton, but I just had a feeling today it would be something more exotic. Okay, so again, 6 things, quarks, we can make hundreds of subatomic particles, and these are things we study in high energy physics. And they have a lot of symmetry, and the whole universe is made up of quarks. Quarks, quarks, neutrinos, mesons, all these particles you can't see drove me to drink, but now I can see them. We don't drink when we do experiments. That's dangerous. But we keep hoping to see individual quarks. People are still looking for them. One of nature's puzzles. Okay, so quantum mechanics is this wonderful other feature that particles can become waves, and waves can become particles. So particles have this dual nature. Sometimes they act as waves, sometimes they act as particles. And this can happen on all kinds of scales. So here I borrowed my wife's knitting needle. Now it looks like a knitting needle because you're seeing it as a particle. In fact, in quantum mechanics, it can become a wave. And a wave can go through things, as you know, right? And if I do this right and carefully, okay, it's acting like a wave today, I guess. That's good. And can it act on the other side as a wave? Yes, I guess it can. Now, that only happens sometimes. So it has this interesting feature. It never knows whether it's a particle or a wave. So that time it was a wave, but then sometimes it's a particle. And it's a it's a problem of deciding which is which. Okay? Okay. We'll do another quantum presentation effect, and then we'll probably wrap it up. Let's see. Okay. Here I have an ordinary deck of cards. No, actually, they're pretty ordinary. Okay, pretty ordinary. Okay, pick a card. No, that's too easy. Okay, pick a card. Pick a card. Just tell me when to stop. Okay, show it to the audience. Don't show me. Okay, put it somewhere in the deck. Okay, so there's your card buried in that deck somewhere. So I'm going to use quantum penetration effect to find your card. So let me get my little prop here. Let me get your prop. So somewhere in the deck is your card. So I'm going to use quantum mechanics to bring that card to the bottom of the deck. Okay? And one of the features of quantum mechanics, first of all, I have to give it some velocity to give it kinetic energy. Okay? So it can come from the middle of the deck to the bottom of the deck. Okay? So let's see if we can do that. Now hopefully that card became a ray, not a particle, and went to the bottom of the deck. Okay? So there it should be. 8 of clubs. Well, maybe I didn't give enough spot. King of spades. Jack? 9 of spades? What? 7 of hearts? 4 diamonds? Jack of spades? 4 king? Where is it? It's not there? Let me go. Let me see my. Well, you know, if I gave it too much velocity, it would have gone through the deck and into the book. Very good. Did you take physics? Did I have you last year? Oh. Yes, there's a card. 7 of spades? Okay. I just got excited, gave it too much velocity. You know, you got to practice these things better. Okay. We can do the atom smasher later. So this is a little effect, another quantum penetration effect I'll do. This I picked up in France last year. And they do a real good job on these. So it's very professionally made. And so again, this is a blade. And it looks like a blade, but again, it can become a particle. It can become a wave. And quantum mechanically, there's some probability that this blade will go through my hand. Now, it doesn't happen too often, but I think today's our lucky day. No, I guess not. Now, if you notice carefully, it's the wrong hand, but that brings up a whole other topic called chirality, handedness of the universe. That's a whole other lecture. But through the magic of microsurgery, we now can connect limbs, of course, and nerves, etc. And let's see if I can. Is there a neurosurgeon in the crowd or micro? But I can restore my hand. Now, people often say, aha, that's, even though it's French made, it's not a real guillotine. So you really should not volunteer for this. That is a real blade. That is a real guillotine. And you can get hurt. So be careful of all things French. So we just did that. So one of the last things I want to talk about is radioactivity. That seems to be in the news these days. Okay. But that's something magical also and can be exploited as noted in nuclear medicine. So when I go to antique stores, though, I look for this stuff. It's pre-World War II Fiesta ware. And there are a lot of fakes around, but I can tell whether it's real or not because I bring my Geiger counter. Now, this is emitting beta particles, so you might be worried out there, but they stop about there, so we're okay. But in my cabinet, I do keep a radioactive sign on it. I also collect old watches, so this is a nice little pocket watch, pre-World War II. This has a dial that stays lit all the time. Modern watches use something else, they're safe. This is a pre-World War II watch with radium in the dial. Okay. I collect those and keep them in a locked lead-lined safe. Okay, but that's an example of nuclear decay, which is another magical property based on quantum mechanical penetration. So what's radioactive here is uranium and thorium ores in that orange glazing. If you come back 1 billion years from now, it'll still be radioactive, but with less radioactivity. It takes about 4.5 billion years for this radioactivity to decrease by a factor of 2. While we're detecting thousands of nuclei decaying per second here, there are 10 to the 22 atoms in there. So only very few of the total number of uranium and thorium in there are actually decaying at any given time. This thing will stay radioactive for billions of years. Well, we can actually exploit that, as long as we don't drink coffee out of it, by using radioactive decay as a tag for dating artifacts. In fact, this is how we know that the age of the Earth is 4.5 billion years old, and the solar system was formed over 100 million years at the same time. Because if we look up here, uranium has a half-life of 4 billion years. It decays through all these other things and ends up in a special isotope of lead called lead-206 right here. So we just have to measure the ratio of uranium to lead, and that gives us the age of the sample, accurate to within a few 10% or less. So this is how we date things that are billions of years old in the solar system. We also have carbon and other isotopes. This technique is called clocks and rocks. I just showed you my Fiestaware. It will be radioactive for 1 billion years. But we could determine how long it had been radioactive by doing this ratio measurement. You can buy a Geiger counter. In fact, you should know how much radon is in your house, because that's a radioactive gas that could be in your basement from decaying stuff out of your walls, because there's uranium, thorium in the walls of concrete. So if you haven't had a radon check, I ask you to do that as soon as possible, and that can be easily mitigated. Radon is the #2 cause of lung cancer in the United States. You should know if you have radon in your basement or in your house in general. Okay, so that's a technique we call clocks and rocks. Hence, we can date the age of the Earth and all kinds of artifacts. Here in Michigan, we have some of the oldest rocks on Earth dating back 4 billion years. Okay, and we know that from this dating technique. And we have all kinds of elements we use for dating and time scales. Okay, amongst other things, it helps us trace evolution to high accuracy. We know we came out of the sea and are evolving. Okay? And we know the time scales. We also know that there were another class of human beings that lived with us years back called Neanderthals. They disappeared. We didn't. Why? But we know when they disappeared, where they disappeared, based on these radioactive dating techniques. And we now know with a high accuracy the course of evolution. And it's interesting, cosmic rays are one source of evolution. Okay, so these quantum penetration effects where involve subatomic particles, including electrons, are the basis for all modern electronics. So my GPS has a computer chip in it. My wife's cell phone has a chip in it. This was the original transistor, and it uses this quantum mechanical wave duality, particle wave duality. Electrons in there behave as waves and can make transitions, and they can be controlled with external circuit. This was the first Bell Lab transistor. This is a more modern chip in a computer that would fit inside your iPhone. It has over 1 billion transistors in it. This is the new era of nanotechnology you may have heard about, and that's what it's all about, packing lots of electronic circuits down to minuscule size and putting in electronic devices. That has revolutionized our life, of course. But you don't have to go to subatomic physics to see nature's magic. As the great philosopher Yogi Berra of the New York Yankees once said, you can observe a lot just by watching. And it's important we tell that to our children and get them off the video games, off of TV, get them outside. I grew up in Minnesota. We had the northern lights. We had rainbows. Unfortunately, we don't have the dark skies we once had, which is unfortunate. But nature has amazing things to observe if we just watch. Okay? So again, let's make this part of our life's dedication. I know I'm preaching to the choir, so to speak. You are interested in science just by the fact you're here, but we have to convey that to some of our friends, and particularly our young people, that they will go into science, maybe make some of these great discoveries, win their Nobel Prizes, improve the lot of mankind, eliminate cancer, etc. Thank you.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.